Can everyone see the paper? I can't see the chat. Okay, great. Thanks. So today I'll be presenting robust agents learn causal world models. And this is a paper from ICLR. I think it's one of the papers that got a best paper award. I'm pretty sure. But I thought I was really attracted to it because it creates a connection between like robust or generalizable agents or policies and then causal models. I don't think that the result is that mind-blowing. Like maybe it's kind of expected, but I think it's really cool that they were able to prove what they were able to prove. The whole paper is theoretical. They have some and actually like the whole paper is proofs, except for a couple of experiments that they do with synthetic data. So I think that there's no real world application for the analysis in this paper. But I think it kind of like opens up, like the math itself opens up, I think, a lot of new room for research. And I think that's what's really cool about it. The work even provides algorithms for identifying causal world models from robust policies. But I think that some of the assumptions of the proofs that they use are a little bit strong for these to be used in practice, and that's why there's no experiment section. But again, there doesn't really have to be because they're proving something that's pretty cool. My goal for this presentation is actually to just, I'm not actually going to go through any of the proofs. All I'm going to do is try to give enough of a background into like decision making and causal learning to explain the theories that they've proved, because it's those results that are more meaningful. So yeah, let's jump into it a little bit. So there's two concepts here. One is robust agents, and the other is causal world models. So in the case of this work, hopefully someone else can let whoever just came in. If not, let me know and I'll switch back to the other screen. I can't see the chat right now or anything. So a robust agent in this case is an agent that is able to make good decisions even when there's a distribution shift, or like what they call a domain shift here. So your environment changes in some way. And then a causal world model, like we all know, like the simplest idea of causality is usually shown with like respect to time, that like one thing happens before another thing. And so what that means is that one thing can cause another thing. So like if I push my glass off the table, it falls onto the floor, and that was caused by me pushing my glass off of the table. And so there's a difference between a causal model of the world, and I think the correct term is like an associative model of the world. So you can create a lot of different relationships. Like you can find evidence that there's like a correlation between a lot of different relationships. I think I saw a funny one, which I'll just like causal is associative. Let's see if we can find the one I was finding here. See, they can find like there's a correlation between the number of people who drowned by falling into pools and films that Nicolas Cage appeared in, like over time. which is kind of, I think is kind of funny. So like, that's an associative relationship. There's a relationship there that, like there's a pattern that seems to exist there, but it's not causal, because Nicolas Cage appearing in films doesn't cause people to drown in pools, I think. And so causal real world models are models that kind of explain how the world works, or a part of the world works. And they're a lot stronger and more useful because of that. Essentially, they can allow us to, if we have a causal world model, and that's one of the results in this paper, then we can adapt to a much larger range of conditions. And a lot of people actually think that in order for us to progress in machine learning, we have to find methods to learn causal models. So like to have even more intelligent models and transformers and things like that, we are going to have to increase our ability to learn causal world models. I hope that gives an explanation of the two concepts. Another thing that's been shown is that causal representations of the world are really key to how humans understand the world. So if we wanted machine learning to mimic intelligence, then we would also want the models that we train, like we learn with data, to learn causal relationships. Okay, so here's the main result of this paper, and we'll go into it a little bit more in a more detail later, but as like a overall, like what this paper is about is that any agent capable of adapting to a sufficiently large set of distributional shifts must have learned a causal model of the data generating process. So there's a lot of terminology in here, but basically what it's saying is that, so say you have a model that interacts with the world in some way. It could be as simple as like you feed in an image of an image and it classifies whether it's a cat or a dog. And then you do things like perform distribution shifts, like maybe you change the color scale of the images. If the model is still able to tell you whether it's a cat or a dog, and you're able to, and when it's saying a sufficiently large set of distribution shifts, so like not only changing the colors, but maybe the scale of the image, I don't know, putting in weird backgrounds, covering the cat or dog partially, all these things, if it can still tell you whether it's a cat or a dog accurately, then it must have learned a causal model of the world. So it must understand what characteristics make something a cat versus a dog in our world. Oh, I see that there's a question, I think. Could someone read that out for me so I don't have to switch back?
Yeah.
So the question, is there some sort of definition of sufficiently large?
Not here. And actually, I think that's one of the reasons why the really interesting algorithms that they use in their proofs to identify like causal models aren't used in experiments, because I think that that's not something that they can. I think in most cases, I think they're just saying that it's like say we have access to all of them, or yeah, there's no definition, but I'd have to go through the proofs further to be very sure of what I just said to you. But even this this result, like this result by itself, is really cool to me, because this result, what it's saying is that, say we have a model that's robust, like it can do what it says it does, and there was no notion of causal learning when we used it, then even though there was no notion of causal learning when we trained it, there was no notion of causal learning when we trained the model, it still learned a causal representation of the world. So like underlying robustness, there must be a causal model of the world. That's what this is saying. And this type of result, yeah, did someone raise their hand?
Yeah, I did.
Yeah.
So in terms of like negating the fact that a model learned a causal representation of the world or a subset. So, for example, given your example, the model that learns whether something is a cat or a dog.
Mm-hmm.
Let's say it is able to distinguish cats from dogs across many different like shifts in
Mm-hmm.
distribution, but there is one or two shifts in distribution, like from 100 different types. Let's say we have 100, 98 different shifts. This model is robust to, but for two of them it isn't. Does that mean it didn't correctly learn the representation, or it's just like an error within?
I think that it 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 might be an error of the model, but just similarly to how humans can make the same mistakes based on the conditions. Like they even pointed out here in their proofs that there are distribution shifts that can lead to a model being incorrect or not being able to identify the causal. There are distribution shifts which can occur which make it impossible to identify the causal structure of the world, whatever. Like the world isn't the actual world like the earth or something. The world is like
Yeah.
whatever information and how it flows and gets manipulated with respect to a task. I'm trying to think of an example, but I, more abstractly, I think you can totally come up with a case where a cat really looks like a dog, even though it's a cat. Maybe like you only see it from behind, um, and so there are cases where even a model that has like we have causal models of the world, or at least that's what our research suggests, and we still make mistakes. So I don't think that it means that it hasn't learned a causal model of the world. Was there another question?
Yeah, I was wondering, do these models have an idea about a temporal component? Is there, I mean, because at the end of the day, a very large data set could be split into different epochs, and you have to shift over the epochs. But of course, if you see the whole data set, it's just a different thing. And I think part of causality is this time component, especially if as a reaction to a change.
Mm. So there's no notion of time in any of this work. In fact, most of the examples they use are like just that of a Sybil classifier with like a set of input variables and an output variable. But I'm trying not to use too much of the language because I haven't gone into it, but
Yeah.
just maybe as a precursor, like the one thing that we've known for a while is that the one way that you can identify a causal world model is by performing interventions and measuring the related variables and the values they take on. And so that's like a necessary condition, and that's what the sufficiently large set of distribution shifts means. Like the only way that you're actually able to identify these models is if you have access to a large number of distribution shifts. And the reason why I say that is because that could be like the temporal shift that you're talking about, how data changes over time. And you need to have those in order to identify the model.
And this agent, what is an agent actually in this sense? Is he capable of doing something, or is it more like a passive? It takes inputs and gives an output.
Let's move on.
Right.
That's a good way to segue into more of an introduction of this paper. So I'm going to do causal models second because Arvid asked about agents, and so let's see. Actually, no, I have to start with causal models because they use it for agents. So they do a couple of different things. Where should I start? I'll start over here. Here's just a lot of stuff about notation. Do I need to explain any of this? Yeah, I guess I do. Okay, so your world, your causal world is composed of a set of random variables v, and they denote like that set by boldface v. And say your world or your causal model is a combination of a joint distribution over these variables, and then a graph G. We'll get into the graph in a second, but what they say is like these models can support associative queries, which is just like conditional queries. So say you have you create you take some subsets of v boldface v. So maybe you say like what's v2 conditioned on v1. You can also figure that out from knowing the joint distribution, which is just trivially true. And then the way that they denote an intervention, which is when you change something about the world, is with this notation like do x equals x here. So the only reason why I'm explaining this is so that you can, when you see do x equals x, just think, okay, that's an intervention. I do think they define agent somewhere, but it doesn't matter. It gets defined later. Okay. So what is a causal model of the world? A causal model of the world is, first it's composed of a set of variables, boldface v, which are the variables that describe the world. And then you have a joint distribution p over them. And then you have a graph G, which describes their, essentially their conditional independencies. So P is a joint distribution that like we see here. And then the graph itself, what it does is it describes like the parents of each variable, such that like the joint distribution using the chain rule can be described using this notation here. So this is a lot of notation to take in at once, but basically it's saying, so like if we want to calculate this joint distribution, we take v1 and we condition it on its parents. I think the best way to understand that is to look here. So this causal model here actually only has two variables, y and x. These we'll talk about in a second, d and u, but y and x. And so y has no parents. And then x, its only parent is y. So if you wanted to describe the joint distribution p x of y, then you would do p of x conditioned on y times p of y. And that's because y has no parent, so it's not conditioned on anything. And x's only parent is y, so it's conditioned on y. And these this graph here where y is pointing towards x, that is the graph that could describe a causal model. Another causal model could be one where x causes y, and they're different. And one key like result or something to know is that if you were just given data that tells you the relationship between x and y, there's no way of knowing whether x causes y or y causes x. The only thing you can really figure out is if there is a pattern between the two of them, but not whether which one is causing the pattern. So yeah, again, not to add too much detail, but the description of a causal model is actually, this is a Bayesian causal model. There's other ones like a structural equations model or Neumann-Rubin's causal model. But this one is like a good one to start with. I agree with it. Okay, so we've described what a causal model is, and then they want to describe What is an intervention, I think? Okay, they describe two interventions. So these are two ways of changing the world, the world such that it changes like how things act within the world. One is by forcing one of the, or a set of the random variables in V, so X and V, to take on a specific value X. That's called a hard intervention. I don't know, like an impossible hard intervention for our world could be that you fix the temperature of the world to always be 23 degrees, which would be quite nice, but impossible. So that's a hard intervention. But then there's such thing as a soft intervention, which is one where you can actually modify the probability distribution of each variable and also its parents. So for example, a soft intervention is could be like flipping this arrow. So y is actually caused by x instead of vice versa. I know this is a lot of, I know I'm going into a lot of detail about this math, but it's just because it's just so we can read out the theories and kind of discuss them, because it's really, the theories are the main point of this paper, as opposed to like the results or some kind of architecture or something. So anyway, there's a lot, soft interventions, as I just pointed out, covers like a huge number of different interventions, like changing the graph, G, this G, or I wonder, let me see. Sorry, I keep underlining stuff and I don't want to underline stuff. Okay, let's see if that, like the graph G, or it could be changing like the distribution of a variable. But so this paper is specifically focused on the case of learning a causal model of the world with the assumption that the causal structure, which is the graph itself, G, doesn't change. Because that's what would be really powerful for us if we had methods where we could learn the causal structure, which we do, but like more effective methods or like more generalizable methods. So they focus on a set of soft interventions called local interventions, which they're interventions that only affect a single variable and not like don't change the graph. So for example, a hard intervention, and what it does is it's a mapping from every single possible value of a variable. So say we have vi and v. This is some one of the variables in our causal world. It takes on values small vi. But what a soft intervention does is it would map those values to, I mean, a local intervention would map each value of vi that's in the of little vi and big vi to a new value. So a hard intervention, for example, maps all of the vi to a constant value to within vi. So it would be like your variable could take on values 1, 2, 3. I'm just going to map them all to 1. That's a hard intervention. But another example of a local intervention could be just like a translation. So the example they give here is changing the position of objects in RL environments. That's probably actually, maybe they should say like robotic manipulation environments or something. But so like if you just change the location of an object, or if you have like a Boolean value for vi, then it would be like a not operation. Yeah, what's the question?
So would, like, given this RL, or as you said, robotic manipulation environment, would removing an object be a hard intervention, do you think?
Removing an object would be a soft intervention, but it wouldn't be so these are local interventions that I'm talking about.
Yeah.
A local intervention, it changes the value of, well, it depends. Okay, if one of the variables in your causal model is the existence of that object or not, so like a Boolean variable like Boolean x here, then removing it would be a hard intervention.
Okay.
because you're just saying it's always not there. But if like the position of that object was a part of your model, that would be a soft intervention because you're essentially removing one of the variables from your model. So the whole causal model is changing.
Okay.
So it depends on what the causal model is. It's a very general structure, and that's what makes these results cool, is because they're like generally applicable. But I think it's also hard to wrap your head around everything. I certainly spent like a really long time squinting and thinking. So we've talked about hard interventions and local interventions, and basically their results all apply for those two types of interventions. They don't really go into soft interventions. Well, they kind of do, but let's just think about local interventions and hard interventions. And then they introduce this idea of a mixed intervention, which is like basically a mixed intervention performs intervention sigma I with probability pi. So now they're denoting interventions by this by using sigma and then with probability pi. So now you could have a mixed intervention, which means that it could be any one of a set of interventions that happens with some likelihood. Just all of this is required for the proof. Okay, so we've gone over causal models. Now let's talk about decision tasks. So I'll just read this out. Decision tasks involves a decision maker agent choosing a policy so as to optimize an objective function. To give a causal description of decision tasks, we use the causal influence diagram. Okay, yeah, I don't have to read out the rest. So let's go to that diagram again. So all of a sudden, a causal model, like I said, would be if we look at A on the left, it's just X and Y. But we usually only care about causal models in the context of trying to accomplish some goal or understand something, to accomplish some goal. And in which case, you make a decision. Like to accomplish the goal, you have to make some decision usually, and that decision gives you some utility. And so that's what they're showing here, which is that like the utility that you gain, this yellow diamond, is affected by the decision you make and what the value y is. So it would be like, say your decision could be like whether this is a cat or not, and y is whether it's actually a cat or not. And your utility is whether it's correct or incorrect. So these causal influence, is that what it's called? Causal influence diagram? Yeah, causal influence diagram like extends the graph G of a causal model and adds in a decision making diamond square and then a utility diamond. And some more information is this dotted line. What it's telling you is that the decision is made solely on observing X, not Y. There would have to be a dotted line from Y to D. And also, if you look at B and C, the black square, what it's saying is an intervention. So it's saying basically like, say you train a classifier to tell you whether something is Y, what value of Y exists. It is taken. Training and test might be different because there's an intervention which causes a distribution shift. And that's what that is saying. And then just see what it's showing you is another causal influence diagram where you actually know the domain shift. So you know how things have changed in your world, and you take that into account when you make a decision. So this is more notation than anything else, but it introduces the idea of a causal influence diagram. I won't go into, is there anything? Oh, I do have to go into policy. But before I talk about policies, Arvid, I think you asked this question, or I think you were asking something along these lines of, like, does the agent interact with the world? So for all of these results, the decision that the agent makes, that's what this unmediated decision task it doesn't affect the world. So all of these results are for the case where the decision you make doesn't affect any of the causal variables in that, well, not any, but like basically any of the causal variables that that are in the model. You have to have a direct link between D and U, essentially.
Yep.
Or you can have additional new causal variables that affect U, but they can't be ancestors of D. That's so. Yeah, you don't affect the world with your decision. You just in a way that could affect the utility. That's one of the assumptions that they have here. Okay. Now, let's talk about what a policy is, because if you remember up here, it says decision tasks involve a decision maker choosing a policy so as to optimize an objective function utility. So the decision maker, which is D over here, they have to choose a policy based on seeing X. So it's a way of deciding something. In math notation, in this paper, they use pi to denote a policy. And your goal is to, maximize your expected utility. And then for every policy, you can calculate, if you know the variables, like you can calculate the expected utility. So that's what this is saying here. And it's short form for this. So expected value of U given that you're using pi. And so the optimal policy pi star is the one that maximizes the expected value of U in the causal model of your world. And there's one last concept that I'll go into before we go into the results, like the three theories, which is the regret. This is a concept that we actually had a discussion about last time I presented, and I didn't remember what the definition was. So this definition comes up a lot, worth knowing. So I'm going to read it out and then just reiterate a little bit. So so what is regret? It's always with respect to a policy. Typically, agents do not behave optimally and incur some regret delta, which is the decrease in expected utility compared to an optimal policy. So difference between your expected utility when you're using the optimal policy and your actual utility. Notice that this isn't the no, I won't go to that. But so yeah, it assumes like, say you have the perfect policy for the information you have. So like there's a policy that given your information on X, you make the best decisions about whether it's a cat and a dog, and then you get the best utility. And then you have worse ones, and your regret is the difference between the two. Okay. Do I want to talk about distribution shift? Let's see if I need to. I guess I do need to say what about assumption two. Okay, maybe we'll come back to this. It's actually not super important for the results. Okay, so there's three theorems here. Theorem 1, Theorem 2, and Theorem 3. Let's go through them. I'm just going to read them out. So these are like the main results of the paper. There's actually nothing else besides these that's within the main text of the paper that's super important. For almost all causal influence diagrams, satisfying assumptions 1 and 2, we can identify the directed acyclic graph G and joint distribution P over all ancestors of the utility function U, given the set of all optimal policies for all interventions. That's what this is saying. All optimal policies for all interventions. So that's saying like if we know the causal model, the utility function, and the utility function, then we can come up. So sorry, if we know the set of all optimal policies, then we can come up with a causal influence diagram, like the correct one. We can recover it, meaning that the key point is the information about the causal influence diagram is contained within these policies if you have this full set. So that means, which means that if you have a set of policies which are sufficiently robust interventions, in this case, it's all of them, so like completely robust interventions, that means that you can fully recover the causal influence diagram, which I think is actually a really cool result. So which means that you can recover the causal model of the world just from those policies. Even those policies are just saying, because a policy, all it's saying is like, okay, give me what the value of X is, I'll tell you what to do. That's it. It doesn't say anything about any of the other variables.
Yeah, it was about the optimum policy is about me changing any of the auxiliary variables that have been that are, yeah, further downstream of the causal structure, right?
Mm-hmm.
Okay, that is interesting indeed. Yeah.
Yeah. So so let me just make sure I'm not being too. So you do have to have information about the values of the parents of D. So in the case of what we've said here, you do need to know X. But basically, as long as you have you know X and D, you can recover the rest.
Yeah, but D is the one thing where I make a decision to act or something, but
Yeah.
I don't interact back with X. So D is purely observational, if you will, right?
Yeah, it affects you, but it doesn't affect anything else.
Yeah.
Or it doesn't affect anything before it. That's okay. So this this is all well and good, theorem one, but there's some pretty strong assumptions here, like for example, that you have access to this infinite set or possibly infinite set. So
And so it because it's said in the theorem, almost all CIDs is what is this almost?
Okay, that's they give some examples in the proof downstream, but basically there are some causal models for which you can't recover, like you wouldn't be able to recover the causal model from data.
Yeah.
Even in this case. They give a good example, but I forget it in the proof. So maybe if we have time at the end, I'll go down and try to find it. But they're like, they're very hard to construct these types of examples where it doesn't work out. Actually, let me scroll down really quick and see if I can highlight it. This is still a. This is what. Yeah, we'll come back to it. I don't. Okay, so the second result, which is actually even cooler than the first result because it's much more practical. Okay, for almost all causal influence diagrams, and like all causal influence diagrams satisfying assumptions 1 and 2, we can identify an approximate causal model M prime given a set of policies which are not optimal, where that you can regret bound the policies. So basically that's what this equation here is saying. It's saying that the regret of, like, the maximum regret of any one of these policies for a specific intervention is only delta or less greater than, or basically the regret is delta or less between the optimal policy and the actual policy. So it's saying if you have a set of policies for which that is true, for which you can bound the regret for all of the different policies, which is much more possible, especially if you have like a finite reward. finite total cumulative void that utility that you could get. Then it's possible to the parameters of M satisfy. Sorry, blah, blah, blah. Okay, so it's then the parameters of M. So basically, the parameters of your causal model satisfy this equation, where this equation grows linearly with regret. So basically, it's saying if you can regret bound the policies that you have access to for the set of interventions, then you can also bound like the error with respect to your causal model, which means that you can approximately recover your causal model even when you don't have optimal policies, given that they're sufficiently good. And then they say later on, if you look in the proof, G, it may not be possible to identify G perfectly. So identify the graph perfectly, as some weak causal relations cannot be resolved due to these error bounds. So like the errors that exist between regret, in terms of regret, lead to cases where like weak relationships aren't identified. So it's kind of saying like, even if you don't have the greatest policy, if it's pretty good, you probably will get like the main causal relationships in your causal model. So that's theorem 2, more practical.
But there's still the policy over in principle infinitely large number of what the sigma was, the
interventions.
Yeah, or it's not really an intervention, right? Because you don't change the variables itself, just the dependent variables, right? So the decision.
No, you can do things like move an object around in the space when you're trying to pick it up, for example.
Okay,
that would be an intervention that's acceptable. But probably an intervention that wouldn't be acceptable, maybe like, or another, it depends on the definition of the task, to be honest, because it changes the causal model. Yeah, and so they've shown that the causal model is recoverable from the policies, from robust policies. And now over here, I think in theorem 3 they just show the other way around to create a sufficient condition. So given the causal Bayesian network, or the causal Bayesian model that is causally sufficient, we can identify the optimal policies for any given utility function and for all soft interventions. And then given an approximate causal model, you can like bound the you can identify like regret bounded policies for it. So it's literally the same results that we saw in theorem 1 and 2, but in the opposite direction. And that's really important because it creates a sufficient condition, which means that like before we were just showing that these results are recoverable, but this way what you're showing is that, like, say you have a causal, both these conditions are true or they're both false. So like if you have a regret bounded set of policies for all soft interventions, that means that you can create like an approximately correct causal model of the world. And if you have an approximate causal model of the world, then you can create like regret bounded policies. And that's the big thing that they did in this work, because they've actually shown in a previous, this result in theorem 3 is well known for the non-approximate case. So like, I guess they also show that it's for the approximate case. This result is well known already here, but they extend it to the approximate case where you don't have optimal policies and perfect knowledge of the causal model graph. So yeah, that's the paper. And I'll just show you one set of results, and maybe talk about some of the implications if I can. But I find that really cool. I hope you guys find it cool too. But so over here, what they do is they show the model average error. So basically, how recoverable the actual causal model was for different regret bounds. So for different, for different regret bounds. So how optimal the policy was. So you can see that as the regret bound decreases, so does the model error. So when they have a 0 regret, so they're using an optimal policy, I guess they still have some error, but it's quite small. So it's like empirical evidence that suggests the same thing as their results. And I think they're using the algorithms that they use as part of their proofs in order to recover the model. So yeah, these are like there's one other set of results that look almost exactly the same as these later in the appendix, but this is just showing empirical evidence of what we just saw. Let's see, I might just end it there for conversation. Yeah, I think I might end it there. That's a lot to swallow. They talk about some of the like this result has implications for agents, for transfer learning, for causal inference. But in my opinion, like while these are good discussions, there's nothing that I read here that I was like, well, this isn't something obvious from the result. So I don't really feel like I need to go through. Yeah, I'll stop there. There's nothing that I want to cover. So yeah, that's the main idea of this whole paper. The fact that we can show like sufficiency between these two things, and that there's like a deep connection between robust policies and learning causal models of the world, which is something that before this there was no result that could prove that connection. It was always speculated but never proven. And so I think that the fact that there is a proof for this now is pretty powerful. We'll see if it leads to anything. I hope it does, because I think causal inference is like really cool, but still kind of a young field in terms of, I mean, there's some problems that have been really heavily studied, but others that haven't. So see where we go from here. Does anyone have anything they want to ask or talk about?
Yeah, I've got a comment, and that is in the introduction, where they say any agent capable of adapting to a sufficiently large set of distributional shifts must have a causal model of the data generating process. And my comment was on the word causal, or the phrase causal model. First read that, I read that the causal model was a correct causal model. And I think what they've shown is you will have learned a causal model that is good enough. So you might have the causal model might have one of the arrows the wrong way around, but in real world data, the causality of these two variables, they're always locked together. So this will all still stand up and work. So the causal model may be wrong, but you can still lean on it because the distribution of data, there's one causal link the wrong way around, but we never actually see, we don't know physics or the environment well enough to know that that's the wrong way around. We never see them the other way around, and all this still stands up, if that makes sense.
Yeah, it's something along those lines.
Sort of implies, right? It's to some extent slightly circular, right? When you say that, I know it stands up because I know my regret must be smaller than delta, and so that the world I fit to it in this causal setting is at least good enough as this delta, so it's good enough for the work. Yeah.
Yeah, exactly. Great paper, Peter.
Really
Yeah,
cool.
it's a cool paper. I want to see if I can find the answer to Arvid's question quickly. They do give an example.
Yeah. I don't have a
Arvid,
very-
I might email you afterwards if I find it at some point. I actually want to go through the proofs because I wish I could present to you guys the causal recovery algorithm set that they showed, but I just did not have enough time. I had to read through like the causal modeling and then decision theory parts twice just to understand them.
Yeah, I don't have a very good intuition about what these interventions, how powerful these interventions are. But I think that this is quite important to. It's really cool to you know, from a philosophical point of view, what can you find out about the world? And that basically tells you, given I can do A, B, and C, I probably can get reasonably close to a right answer.
Yeah. Great. Well, if there's no more questions, then we'll stop there. And thanks everyone for coming. Hopefully we'll see you here next week and have a good weekend.
Thank you very much.
Thank you.
Thanks a lot.